Okay, we're continuing with chapter 6 of the trigonometry textbook. We just learned about the inverse trig functions. Now in this video, we're going to go through section 6.2, which is the first part on trigonometric equations. And the next section is part 2. Now, we're not referring to equations that contain inverse trig functions. That we're going to learn about in section 6.4. All right. Earlier, we studied trigonometric equations that were identities. We now consider trigonometric equations that are conditional. These equations are satisfied by some values but not others. So, yeah, it's not like we haven't seen any trigonometric equations up to this point. So that would be an equation that contains a trig function, because that's what every single identity we just talked about in the previous chapter. All of those identities were equations with trig functions in them, right? So what are we talking about here when we say trigonometric equations? Well, remember from algebra, an identity was an equation that when when you went through solving the equation, you subtracted variable terms from both sides, etc. You wound up with something like 5 is equal to 5, and you could subtract 5 from both sides and go all the way down to 0 is equal to 0. What that meant was that the equation was satisfied for every single value of x as long as it was within the domain of everything in the equation. And that's what was called an identity. And that term is the same term here for the trig identities, because remember, for a trig identity is valid for every single theta that you could, that's all, as long as it's within the domain of whatever's in the trig functions. It's satisfied. Okay? So, but in algebra, if the equation wasn't an identity, then there were two other possibilities. You could get something like 0 is equal to 5, in which case that's not true, and that meant that there were no solutions to the equation. There was no x you could plug in that would satisfy the equation. That was called a contradiction. And there was also the case of conditional. The equation was conditional, and that's what we're studying here. That's what we're referring to as a trigonometric equation. It's an equation with trig functions in it but with the equation being conditional. In the case of conditional was that you had, most of the time in algebra, it was like you had one or two unique solutions. X is equal to 5, but like for quadratic equations, you could have two solutions. You had just like a finite number of solutions. But the technical definition of a conditional equation is that these equations are satisfied by some values but not others. So we're going to see with trig equations, technically there's going to be an infinite number of solutions because the trig functions are periodic, but it's still conditional because it's satisfied by some values but not others. An identity is satisfied by all values within the domain. Conditional is satisfied by just certain values. Okay, so that's what we're referring to here. And then also in section 6.4, when we talk about equations that involve inverse trig functions, it's the same idea. You're going to have an equation with inverse trig functions in it, but it's a conditional equation. All right, linear methods. The most basic trigonometric equations are solved by first using properties of equality to isolate a trigonometric expression on one side of the equation. So properties of equality, subtracting or adding the same thing to both sides, multiplying or dividing the same thing on both sides, things like that. So, all right, solving a trigonometric equation, linear methods. Solve the equation 2 sine of theta plus 1 is equal to 0. And then, but over the interval from 0 to 360, that's part A, and then for all solutions. So, okay, we've got 2 sine theta, 2 times sine theta plus 1 is equal to 0. Okay, so what we want to do is isolate the trig function on one side and then everything else on the other side. So, and you can imagine this could get more complicated in the sense that maybe you can't isolate just a single trig function on one side with just like constants on the other side. And that's what they're referring to as linear. It's set up to where we can subtract 1 from both sides and then divide both sides by 2. And now we've got trig function on one side and a constant on the other side. So this is what's linear. If it was the case where the best we could do was get like sine theta plus cosine theta is equal to something, then that's a more complicated equation. It's not linear. Okay, so now what do we do here? Well, we're trying to solve for theta, right? That's the idea, that we're trying to solve for the variable here. So how can we get the theta out of here? Well, we use the inverse of the sine function. That's the inverse sine function. So we take the inverse of both sides of the equation. So inverse sine of sine theta is theta. And on the right side, we've got inverse sine of 1/2. Okay, so now we know how to evaluate inverse trig functions. We just did this. And so we're asking, what angle, when you take the sine of that angle, do you get 1/2? So, okay, when we think about 1/2, we can think about this is a simple setup here with the 45, 45, 90 triangle. So one root 2, or no. This is a simple setup with the 30, 60, 90 triangle, because we've got one root 3, 2. So what is the sine of 30, opposite of our hypotenuse, is 1/2. Okay, but now remember, with inverse trig functions, you have to think a little bit deeper than just this basic solution. We can't just say this is equal to 30 degrees. That's only part of the story, because it works out to where we have to think about. So you might say, oh yeah, so it's going to be 30 degrees, but also any angle that's coterminal with 30 degrees. Yes, that is true, but actually it's more than that. There's going to be, when it comes to inverse trig functions, there's going to be two angles from 0 to 360 that satisfy the inverse trig function. Two angles. Well, okay, actually, I'm actually not stating this right. I'm sorry. So, okay, actually, yes, this is technically correct here, as far as the statement. Yeah, okay, I want to make sure we get this right. This statement right here is actually exactly correct. And why is that? What did we learn in the previous section? Well, when it comes to inverse sine, the range is from -90 to 90. So if we type this in to the calculator, we're in degree mode, inverse sine of 1/2, 30 degrees. So this statement right here, that inverse sine of 1/2 is 30 degrees, that's exactly right. However, in the context of the original question, what's this asking us? What angle, when you plug it in, do you get? And you say sine of that angle times 2 plus 1 is equal to 0. What angle? What satisfies the equation? It doesn't. Any angle. It doesn't matter what it is, unless specified otherwise. Like in part A, they specified that the angle is only between 0 and 360. So in that case, even though this is true, this statement is true, remember the inverse trig functions, they're set up to where they act as functions, to where there's one output corresponding to every input. But that's kind of like a tool that we use so you would, in the sense that you want to, so we got the inverse sine of 1/2 is 30 degrees. Okay, but we want to consider that, okay, but the question that the inverse sine is asking is, what angle, when you take its sine, do you get 1/2? We want to think about that question in general. What are all the angles that satisfy that? And there's going to be, when it comes to the specifics of the problem we're trying to solve, there's going to be, that one of those angles is going to be applicable. You have to look at the specifics of your problem. Now, if it's just a trig equation like this, where there's no underlying problem, well, then you just answer the question. You state all the solutions, or you just state what the limited number of solutions based on what the question asked you. But for a real-life problem, you're going to get the theta that solves the equation, and then you're going to consider, okay, what are all the potential solutions to the equation? And then think about, okay, well, which one is applicable for my problem? That's what you're going to do. So how do we know? So, okay, what are the other angles that when you take the sine of that angle, you get 1/2? Well, okay, it's any angle that's coterminal with 30 degrees. That's true. But it's also going to be another angle within 0 to 360, and all angles coterminal with that. So, okay, sine is positive in the first and the second quadrants, right? That's the y coordinate. So And also is going to be a solution to this equation is going to be an angle that is in the second quadrant that has reference angle equal to 30 degrees. So 30, 60, 90 triangle. We've got, let's see, 1 root 3, 2. So this angle is 150 degrees. So, you know, the answer to part A is 30 degrees and 150 degrees. That's the answer to part A. The answer to part B is 30 degrees, 150 degrees, and any angle coterminal with 30 and 150. You plug in 150 into this equation, it's going to sine of 2 times sine of 150 plus 1 is equal to 0. 2 times sine of 30 plus 1 is equal to 0. And then also any angle coterminal with either of those. Okay, so that was the linear method. Now we're looking at the zero factor property method. So solve sine theta times tangent theta is equal to sine theta over the interval from 0 to 360. So let's see. We've got, how would we solve sine theta times tangent theta is equal to sine theta? We could divide both sides by sine theta and get tangent theta is equal to 1. So why are they calling this? Oh, okay. Yeah, I see. No, you don't want to do that because it's like in algebra, if you had x to the 4th is equal to 8x. Okay, you might say, let's divide both sides by x, get x cubed is equal to 8. Take the cube root of both sides. X is equal to 2. That's a correct. X is equal to 2 is a correct answer. But if you have to be careful with equations when dividing both sides by like x or multiplying both sides by x, because then x can't equal 0. So you could be missing a solution in the sense that, so okay, we have this. The way you want to solve this, it's like a polynomial equation. You want to bring everything to one side, and with the other side equal to 0, then factor the left side, okay, and then now use the zero product property. So you have x cubed minus 8 is equal to 0, so x is equal to 2, but you also have x is equal to 0, so there's two solutions. When we divide both sides by x, we eliminated the x is equal to 0 solution. So how do you recognize when this could happen? Well, we started with sine theta times tangent theta is equal to sine of theta, right? And we divide both sides by sine of theta, that's fine. But okay, for what values of theta is sine theta equal to 0? Well, okay, when theta is equal to 0 or when theta is equal to 180, and then any coterminal angles with that. Well, okay, we've eliminated that theta. And now with this, whatever solution we get here, theta is not going to be equal to 180 or 360 or any angle coterminal with that, because we can't divide by 0. And so, but it could. Okay, but the thing is, what if in the original equation, if we plugged in theta is equal to 0, theta is equal to 360, and we get and that's a solution. We want to state that as a solution, right? And actually, we can see that sine of 0 is 0. So you have 0 on both sides. Tangent of 0 is 0. So when you plug in theta is equal to 0, you get 0 is equal to 0. And same thing with 180. So that is actually a solution. So what we're going to do is, it's the same idea. We want to, as a polynomial equation, we want to bring everything to one side before we consider dividing by 0. Consider doing this, or dividing both sides by something that could potentially, whatever we're dividing by could be a potential solution. We bring everything to one side, set it equal to 0, and factor, or no, it was, now we've got sine theta times, we can factor out sine theta, and there we go. Now we've got, so when sine of theta is equal to 0, that's going to be a solution. And when tangent of theta minus 1 is equal to 0, tangent theta is equal to 1, that's going to be a solution. So now we solve this equation, inverse sine both sides. So you've got theta is equal to inverse sine of 0. And then here you're going to have theta is equal to inverse tangent of 1. And so you need to go through the same process of, okay, for what angle when you take its sine do you get 0? Well, that's going to be 0 and 180, and any angle coterminal with those. Well, okay, well, they just went over the interval from 0 to 360, so 0 degrees and 180 degrees. Okay, now what about inverse tangent of 1? Well, we think about the 45, 45, 90 triangle, which 1, 1, root 2. So tangent of 45 is equal to 1, but, okay, so 45 is an answer, but tangent is positive in which quadrants? In the first and the third. So in the third quadrant, what angle has reference angle 45 degrees? That's going to be 1, so 1 root 2. This is minus. That's going to be 225. So 225 is also a solution. And any angle, and then if you want to go past 0 to 360, you could say any angle coterminal with these 4 angles. All right, caution, trying to solve the equation in example 2 by dividing each side by sine theta would lead to tangent theta is equal to 1, which would give theta is equal to 45 or 225. But the missing 2 solutions are the ones that make the divisor sine theta is equal to 0. For this reason, we avoid dividing by a variable expression. Yeah, exactly. Okay, now quadratic methods. The equation AU squared plus BU plus C is equal to 0, where U is an algebraic expression, is solved by quadratic methods. Yes, the expression U may be a trigonometric function. Yeah, so what they're saying is that we could, there's scenarios with trigonometric equations where you could put the equation into a form that mirrors a quadratic equation. So you have, if you have something like, if you could put an equation in a form like this, tangent squared x plus tangent x minus 2 is equal to 0. So we've got tangent squared x plus tangent x minus 2 is equal to 0. You could say that u is equal to tangent x. And so therefore that means that you have u squared plus u minus 2 is equal to 0. Now this is a quadratic equation that we learned to solve in algebra. So we factor this. You've got let's see, 2, 1, plus 1 minus, or plus 2 minus 1 is positive 1. Okay, so you have u plus 2 is equal to 0, and u minus 1 is equal to 0. So u is equal to minus 2, and u is equal to 1. So now, but u is equal to tangent x, so tangent x is equal to minus 2, and tangent x is equal to 1. So now you see that x can be inverse tangent of minus 2, or x can be inverse tangent of 1. And then you just go from there. There's going to be 2 solutions here between 0 and 360, 2 solutions here between 0 and 360, and then if you expand out from there, it's any angle that's also coterminal with those 2 angles. So here we're going to have 4, between 0 and 360, there's going to be 4 total x values, because you'll have 2 here and 2 here, and they get, let's see, I mean, we can, let's go ahead and we can get them, why not? So, and they're going to be, so let's see, it'll be, they give it in radians, there's the angles, between 0 and 2 pi. But that's the only thing that was asked, between 0 and 2 pi, but that's the 4 solutions. But technically it would be, and if you want to be fully, have the full potential solutions, it would be any angle that's also coterminal with these 4 angles. Okay, what about this? Cotangent x. So, okay, we've got, let's see. cotangent x Okay, so let's solve this. Well, let's just try and isolate the cotangent on one side, but it looks like that's not going to work. But, okay, we subtract 1 from both sides. We've got this quadratic form here. So if we say that u is equal to cotangent x, then you've got u squared plus 3u minus 1 is equal to 0. Now, what they're going for in this problem is that you can't just factor this. So you end up having to, well, how do you solve a quadratic equation that you can't factor? Well, there's different ways. You could complete the square or the quadratic formula. So u is equal to minus b plus or minus b squared minus 4 times 1 times minus 1 all over 2 times 1. So minus 3 plus or minus, okay, no, this was a minus 1 here. 9 minus, so 3b squared minus 4 times 1 times minus 1. So that's 9 plus 4. So okay, so there you go. Now, but u is cotangent x, so cotangent x is equal to, you've got minus 3 plus root 13 divided by 2, and then you've got cotangent x is equal to minus 3 minus root 13 divided by 2. And now, so here you could take the inverse of both sides, but it's not going to be some simple where you can use the 30, 60, 90, or 45, 45, 90 triangles. You'll have to use your calculator. And then, so you get, let's see, we could say, so, okay, let's do one of these. So if we take minus 3 plus root 13 divided by 2. Okay, so that's inverse cotangent of this. That's what we're doing here. So x is equal to, okay, so we're in degree mode. So cotangent, I think that's 0 to pi is that, or 0 to 180 is the range. So we should get something between 0 and 180 here. We're in degree mode, but it's not going to be a nice round angle. So 73.155, okay? But then you go further though. So what cotangent is positive in quadrant 1 and 3, just like tangent. So is minus, okay, hold on, wait. Minus 3 minus root 13 divided by 2, that's actually a negative value. Wait, what did we just do? Oh, okay, no, we did, okay, it switched it on me. This was minus 3 plus root 13 divided by 2, which is a positive number. So we're doing this one here. That's a positive number, so that makes sense. We're in the first quadrant because cotangent in the first quadrant is positive. So cotangent is also positive in the third quadrant. So what angle in the third quadrant has this as a reference angle? Well, you just add 180 to this. And there you go. That's the two x values that satisfy this equation. There's two more that are going to satisfy this equation, and that'll be the 4 answers, unless you expand out between past 0 to 360, and there will be any angle coterminal with those. Okay. Now, trig identity substitutions. Recall that squaring each side of an equation, such as this here, will yield all solutions, but may also give extraneous solutions. So yeah, what they're trying to illustrate is that, so okay, we just solved a quadratic form, but we're not going to go any further than that, but you can extend this principle to any kind of equation that we solved in algebra. Like if you have an absolute value equation that involves trig functions, well then it's the same idea. You kind of pattern match just like we did with the quadratic. Like we could, based on what we just learned here, we could solve a polynomial equation higher than degree 2 using these same principles, you see? So we're going through all of the scenarios that we come across in algebra, the unique scenarios. That's what we're doing. And then, so does that mean we're going to, every single type of equation that we cover in algebra, we're going to go over here? No, there's no need to do that. They're just giving us some examples. And so if we had something like a radical equation with a trig function, or a polynomial, or whatever, any kind of those equations, a log equation, whatever, it's the same principles. You just kind of, you can match up the patterns and solve. Match up the patterns between the regular algebraic equation and the trig functions that are in the equation, and solve it. Just like we're doing here with where we kind of paralleled a quadratic equation. Okay, so here it's the idea of, now they want to talk about the idea of extraneous solutions. Remember, with a radical equation, you could get extraneous solutions because of the process of squaring both sides. Not because of so much because of the radical, but because of the process of having to square both sides. Extraneous solutions come out of that. Just kind of like in with absolute value equations, there could be extraneous solutions, not because you're squaring both sides, but just because of the nature of the absolute value. And so in that case, you would think that if you had a trig equation that had absolute values in it, you'd have to look for extraneous solutions, potentially. Okay, so solutions that satisfy the final equation, but not the original equation. Exactly. You get these solutions, but then when you go plug them back into the original equation, it doesn't satisfy it. But there's two cases where this could happen. There could be domain issues in the original equation. You could solve, get a solution, and then come back and plug in the solution, and you're taking the root of a negative number. That's one case. But there's also the case where there is no domain issue, but it still doesn't satisfy it. That's called extraneous. All right, as a result, all proposed solutions must be checked in the original equation. Exactly. There's certain types of, in algebra, there were certain types of equations where you actually had to check the final answer. You had to. Not because you might have made a math mistake, but because even if you did everything correctly, it could be the case that the answer doesn't check. That was for domain issues, like, with a rational equation, you could be dividing by 0, and it could be the case that you go back to the original equation and you're actually dividing by 0, even though you got that answer. But then there's also the case of just extraneous solutions, like with radical equations where you square both sides to get rid of the radical. Okay, so, all right, with that, then, let's see, they say, so this equation here, tangent x plus root 3 is equal to secant x. And so this is an issue because we want to isolate a trig function, right? So what do? Like if we've got that, this comes up when we have multiple trig functions instead of just one. If we just had one trig function, or we could get it into that form easily, then that would make it linear. We just looked at examples where we have multiple trig functions, and we could kind of solve them by factoring, bring everything to one side, factoring and using the zero product property, or doing like a parallel to another equation, another type of algebraic equation like a quadratic equation. But we can't really do that here, right? There's no, we're stuck. There's no parallel to a certain type of equation that we can use. We don't really know what to do. This doesn't kind of match up with a form of a type of algebraic equation we know how to solve. So what they're saying is that we can think about, is there some way we can create a trig identity out of this? And we know that tangent and secant are related with tangent squared plus secant squared, or no, 1 plus tangent squared is equal to secant squared. So maybe we could square both sides here. And that's fine, but anytime you square both sides of an equation, you have to think about extraneous solutions. That's just something to keep in mind. So, all right, you have tangent squared of x plus root 3 tangent x plus root 3 tangent x plus 3 is equal to secant squared x. Okay, and let's see. Now, what they did was they went ahead and transformed this into 1 plus tangent squared x And that works out because now you can subtract from both sides tangent squared of x. And so, okay, that's great. Now we're going to be able to solve it. So 2 root 3 tangent x plus 3 is equal to 1. So subtract 3 from both sides. You get this is equal to minus 2. So tangent x is equal to minus 1 over root 3. That's minus root 3 over 3. Okay. And this is just another way you can think about solving trig equations. If you can't figure out what to do, if there's no kind of obvious pattern you can match up with their algebraic equation and whatnot, or just bring everything to one side, factoring whatever, then just manipulate it. Just start, square both sides. Just just start playing with it and seeing if you can get some trig identities that can simplify it. Just play with it, right? And so, okay, here it's same thing. You're going to get 2 solutions between 0 and 360, and that's it. And there would be any angle that's coterminal with those 2. And you might be wishing I would actually go through the process of getting the angles. We'll do that in the next video. We're going to solve a bunch of trig equations, and for each of those problems, we'll go through the full solution. Okay, so solving a trig equation, first decide whether the equation is linear or quadratic in form in order to determine the solution method. So yeah, analyze the form. Analyze the form. Can you bring everything to one side and factor? Is it just linear to where you can just, like this was linear. Once we applied the trig identity and got to this step, then it became linear. So just identify the form. What kind can you match it up with, like, mirror it with another type of algebraic equation, quadratic, polynomial, whatever, absolute value, whatever? Could you maybe manipulate it and use some trig identity to simplify it? So yeah, in the next video, you'll get a good sense for the procedure for how you approach to solving a trig equation. All right, here's an application. So describing a musical tone from a graph. A basic component of music is a pure tone. The graph in figure 26 models the sinusoidal pattern y is equal to p in pounds per square foot from a pure tone at a time x is equal to t in seconds. So, okay, let's see. The frequency of a pure tone is often measured in hertz. 1 hertz is equal to 1 cycle per second and is abbreviated hertz. What is the frequency f in hertz of the pure tone shown in the graph? So I guess here we've got 0.04 seconds, and there's, let's see, 1, 2, 3, 4, 5, 6. So 6 cycles in 0.04 seconds, 6 cycles in 400th of a second. So we've got 150 hertz. Okay. Now, the time for the tone to produce 1 complete cycle is the period. Approximate the period in seconds of the pure tone. Yeah, so we talked about all this before. The period is going to be 1 cycle is what's the time for that. So if it's 0.04 divided by 6, so, or the reciprocal of this, 1 over 150th of a second, or no, 150th of a second. 1 over 150 seconds. That's the period. Okay. An equation for the graph y is equal to 0.004 sine 300 pi x. Okay. Yeah, for this graph. That's an equation for this graph. Use a calculator to estimate all solutions that make y is equal to 0.004 over the interval. Okay. So yeah, this is an equation for this graph. And then over the interval they zoom in from 0 to 0.02. They zoom in on 3 cycles. Use a calculator to estimate the times. So it's weird. Right now, we're using a sinusoid where the input is time, not angle, which is, it's a little weird to think about. But so we're thinking, what are the times that result in the amplitude of 0.004? So you're asking, you set y is equal to 0.004. And so what you're going to get is sine of 300 pi x is equal to 1. You divide both sides by 0.004, and so you're just saying that 300 pi x is equal to inverse sine of 1. X is going to be time in this case, and it's the same idea. It's just going to be, but we're only the, so yeah, this is a little bit different in the sense that, so we could look at this. Let's see. We've got the x inputs that they're looking at is just from 0 to 0.02. Okay, so when we think about inverse sine of 1, we've got, so, well, that's a quadrantal angle, which makes sense because we're at the amplitude. So positive 1, let's see, sine is positive 1 at, well, okay, in this case, there's only one angle between 0 and 360 that makes sine positive 1. So I take it back. There are certain quadrantal angles where there is actually only one angle that satisfies the inverse trig function between 0 and 360. But if that quadrantal angle results in a trig function being equal to 0, then there's 2. So quadrantal angles are a little bit confusing. But any angle that's, if it's not a quadrantal angle, there's always, with inverse trig functions, there's 2 angles between 0 and 360 that answer the question of the trig function. So I hope that's not too confusing. I don't think I stated that correctly in this video and the last video. Like with an inverse trig function, there's only one value of an inverse trig function because it's a function. But then if you're thinking about it in general, the question that the inverse trig function is asking, then there's going to be 2 angles between 0 and 360 that answer that question if it's not corresponding to a quadrantal angle. If it does correspond to a quadrantal angle, then in some cases it might just be one angle, or in some cases it still might be 2 angles. It just depends, but quadrantal angles are a little bit different. In this case, it's just going to be 1 because there's only one angle between 0 and 360 where when you take its sine, you get positive 1. That's the 90-degree angle, because here's negative 1, and that's it. But if you have the inverse sine of 0, there's 2 angles between 0 and 360 that when you take their sine, you get 0. That's 0 and 180, because sine of 180 is also 0. So it's a little bit different with quadrantal angles. But okay, so it's 90 degrees, but it's also any angle coterminal with 90. So we've got 300 pi x is equal to, and this could be 90, this could be 450. And it's interesting because, well, which one is it? Well, it's in this case, it's more about what's going to result in an x that's within the domain. So this is pretty interesting. You see? So if we chose 90, that's fine. But then what happens when we solve for x? If we're using 90, so you get 90 over 300 pi, so that's 9 divided by 3, 30 divided by 3, that's 3 over 10 pi. And what is that? .095. And no, that's not within the domain of what we're looking for. So, well, no, okay, wait, this would be, we're in radians here. Yeah, sorry. So it would be, you'd have pi over 2, or maybe, let's see, 2 pi plus pi over 2. So that would be 4 pi over 2 plus pi over 2. That's 5 pi over 2. So, okay, so let's see. We've got pi over 2 divided by 300 times pi 0.0016 0.017. There's one answer. But then what about if we do this with 5 pi over 2? That's also an answer. And then we could keep going, and so there's going to be actually 3 answers here, you see? So, yeah, this is actually really interesting. This is a great example of how the different potential answers you can get when using inverse trig functions. It wasn't that the values of the inverse trig function weren't directly related to what you were looking for. You had to do a little bit more algebra to see which of those angles were applicable.